Yeah, the next topic that we're going to talk about are binary search trees. And as the title indicates, they're used for searching, okay, for elements. And let's see how we organize a binary search tree. A fundamental property of binary search trees, which is a binary search tree, is also a binary tree with a difference. And what is the difference that we have? And the difference is the following, that every element in the binary search tree, every element in the binary search tree is unique. Sorry, is unique, and this is like the job ID that I was talking about with respect to priority queues. And another property is that there is a order in which elements are placed in the tree. So formally, a binary search tree is a binary tree it may be empty, just like the binary tree. If it is not empty, it satisfies the following properties. Every element has a key and no two keys are identical. But this is similar to the hash table, where the original key is not identical, but the hashed value can be is identical, but the hashed value can be the same. So what do we mean? Keys are unique. The keys in a non-empty binary search tree still have the following property. That keys in the left subtree are smaller than the root, and the keys in the right subtree are larger than the root. Okay. And the left and right subtrees are also binary search trees. Binary search trees, as the name indicates, are used for searching / insertion / deletion of nodes, and we will see in a while that the time complexity of these operations is order of h plus 1. This again is similar to a binary tree, but order must be preserved. And also, a binary tree need not have unique keys. Okay. So now, sorry. One moment. Yeah. Let us look at what are the operations that we perform. STR, insertion, deletion, and search. Let's take some examples. This is an example. Let's say this is the root. All elements on the left side of the root are smaller than the root, and all elements on the right side of the root are larger than the root. And also note that every node is a binary tree. Suppose I start. So this is the left subtree. And again note that all the elements on the left subtree are smaller than the root. This node has no right child, but nevertheless, a binary tree can be empty. Therefore, the right subtree is empty over here. Similarly, 10 here, and notice that all its children in left subtree are smaller, right subtree are larger. 9 again has a left subtree, no right subtree, and so on. And these correspond to the leaves of the binary search tree. Now, interestingly, binary search tree can also be something like this. 6, 1. This is a skewed binary search tree. Okay. So how do we search? So basically, why do you say skewed? Because this tree, for example, the heights of the left and right subtree where the same, and whereas here the height of the left subtree is 4 by the height of the right subtree is 0. Okay. Now, okay. Now there are, when we come to skewed binary trees, there are some interesting problems that we can solve. And how do you find the height of the tree? How do you find the height of a such tree? Or even a binary tree, for example, the Huffman coding problem. Height can be important because it tells you how deep you have to go to, you need to travel to find the code. Okay, I'll take some examples in the lab class. And these are the various things that we have. So we said we can do insertions. So operations, we talked about, operations. Yeah, insertion, deletion, and such. So first, of course, we need something to create an empty binary tree. We may also need to create a binary tree with a single node and then we want to insert X into the search tree. We want to delete X from the search tree and so on. So let's see how we insert, okay? Let's say I want to, now let me take a smaller tree. Let's say I have 5. I have 5 here, 3, 1, and let's say it's 4 here. This is 10. This is 7, 6, 8, and let's say I have 15 here. Let's say I want to insert 9 into the tree. Okay. So how do we do? We start with the root and we insert it at its, so I go down the root, start with the root here. I'm taking an existing binary tree. We'll see how to construct a binary tree from the scratch. So I insert this. So what do? I'm looking at inserting the key 9. Okay. So I start with this. I notice that it's larger than the root, therefore it has to be on the right subtree. Then I compare one level down. Now it is smaller than this node, therefore it has to be on the left subtree, but it's larger than 7. Therefore, I come down this, and it's larger than 8. Therefore, we insert it as the leaf node of 8. 9 will be the initial position of this tree. So now let's do one thing, okay? Suppose we were given a set of elements. Let's take these set of elements that we have. So this is how you insert a new node into the tree. Let's go through this process for a set of elements. Suppose I want to insert these elements starting from an empty tree. So you create an empty tree. And so this is the first node that I see. I make this guy the root. Okay. Then I see the number 3. It's smaller than 5. So I insert it as the left child of 5. Then I see 1, start with the root again. Compare with 5, compare with 3. It's smaller than 3. Therefore, I insert it as the left child of 3. Similarly, I come to 4, compare with 5, compare with 5, compare with 3. It's larger than 3, therefore it becomes the right child of 3. Then I see 10. 10 is larger than 5, therefore it becomes the right subtree of 5. Now I see 7. So it's larger than 5 and smaller than 10, larger than 10, larger than 5, smaller than 10. Therefore, it becomes the left subtree of 10. Then I see 6. Again, I do the same thing. 6 is the left subtree of 7. Then I see 8. 8 is smaller than 10, but it's the right subtree of 7. And finally, 15, which is the larger than 10. So what did we observe in the process of construction of the binary search tree? Given a set of unordered numbers. What did we see? Now, given a set of unordered numbers, what did we see? Every time, notice that the first number becomes the root. And every new number, so root is also a leaf here. Initially empty binary tree, and you're inserting the first root node, which is also a leaf. Okay, it's always getting inserted in the leaf. Then again, 3 gets inserted in the leaf. Then 1 gets inserted in the leaf. 4 gets inserted in there as a leaf node. 10 is the leaf node of 5. 7 is the leaf node of 10. 6 is the leaf node of 7, 8, and so on. Okay. So always a new node gets inserted as a leaf node. Okay. Now let us try to do some traversal and see what you find on this. Suppose we performed in order traversal of this tree. What will we get? So we come down, leaf node first, 1, 3, 4, 5, 6, 7, 8, 10, 15. Isn't this nice? So in order traversal gives us the sorted order, okay, of the keys in the binary search tree. So important point to remember, when we construct the binary search tree, we are inserting always gets inserted where leaf node. So now you can see a nice application of BST is a dictionary. Okay. So the problem with this, now how long will it take to retrieve an element from the tree? I want to get some properties. So maybe 6 corresponds to a dictionary element. Find the means. Then you notice that you have to do 4 traversals. Now consider this other example where we had, let's say, 6 went up to 1 over here. So here, so we had to make comparisons with 8 different nodes. In case the you're looking for something, in case we are looking for, we need information about. Okay. Again, in order, what will it give you? It will give you 1, 2, 3 up to 8. So the drawback of the binary search tree, whether it's search or insertion, because insertion is done only at a leaf node, the complexity is of the order of height plus 1 of the tree. Why height plus 1? Because n minus 1. So there are n nodes, the maximum height that a binary search tree can have, height is h plus 1. Assuming that there are maximum height is h, which is, h, and this is n minus 1, and number of comparisons, maximum number of comparisons to retrieve an element to be made is h plus 1. Okay. Now, let us look at the next job of deletion. So let me recopy the tree over here. 5, and I have 3, 1, and 4. 1 and 4. And then I had 10 over here. 7 and 6, 8, and 15. Now let's look at binary search tree deletion. So how do you perform the deletion of a binary search tree, deletion of an element in a binary search tree? Let's say I want to delete, I want to delete 10 in this search tree. Okay. Now we have to ensure that upon deletion of the node, the BST property must be satisfied. Okay. So let's see how we ensure this. Okay. So now, which node should? So deletion of 10, it's no problem. I look for the key 10 starting from the root. Root is your entry point over here. And 10 is greater than 5. So I want to remove this entire record corresponding to 10. Now, which should it be replaced by? The BST property should not be violated, as we already said. So which element that replaces 10 will ensure that the BST is not violated. Okay. Now, there are two choices that are available. Level. And these are largest child on left subtree or the smallest child on the right subtree. Right? Why so? In this example, I can replace 10 with 8. Yeah. Or I can replace it with 12. Both of them will ensure that the binary search tree property is not violated. Now, suppose, this one had a left subtree 7.5, which had a right subtree 7.75. All those integers, I'm just making a modification here to show what happens. So now what we have to do is we have to ensure that I can take this node and no problem, I move it here. But then this guy has a left subtree. Will it have a right subtree? No. Why? Because it's the largest element on the left subtree. Similarly, if I take 12 here, will it have a left subtree? No. Why? Because 12 is the smallest element on the right subtree. Okay, there's no element smaller than that. Then what we have to do is we have to ensure that the binary search tree property is not violated. So that's good. I can take this. I put 5 here. 3, 1, 4, 10. 10 is gone, sorry. I replace it with 8. No problem. 7, this is not violated. I have 6 over here. Now I have a left subtree of this guy. That's possible, right? Because 7.5 and 7.75. So then what do? I make these the right subtrees of the 7.75. Okay. And then the binary search tree remains properly. Note that in deletion, important point to note is that in deletion, what are we doing? We are taking a given node, we are replacing 10. So now 10 has to be deleted. So I take the largest element on the right subtree, which is 8. It has a left subtree 7.5 and 7.5. Although I said integers, I've introduced two numbers because I don't have any space for integers in here. Two numbers which are smaller than 8 but larger than 7. So just to show what happens to that subtree. So now when I take this guy, take this 8 over here and put it over here. Now this one's left subtree needs to be attached. So where do? I go and attach it to the parent of this particular node. It's a little bit of a complicated operation. Okay. Similarly here, 12 can have a right subtree. For example, 12 could have a 13 here. If I'm replacing with 12, then clearly that will become the left subtree of 15. So I can use either choice for either way to delete a node in the binary search tree. So just let's recap what we did. And search is of course very straightforward. I start with the root. You want to find, go down, and if you have reached a leaf node and you do not find the key, searches, start from the root, descend down the tree, and you reach a leaf node. Either you find a key somewhere, find the key, or you reach a leaf node which is also not key, and you return. So if you look at it, the operations of insertion, find, and deletion are all order height of the tree. Okay. So there's one drawback of the binary search tree that, as we saw in some examples, it can become terribly skewed, can become horribly skewed like this. And one of the big problems is, how do we balance the binary search tree? Before that, I want to take some small problems generally on binary trees. I mean, basically programming problems. Binary trees lend themselves to recursion very nicely, and we'll see some examples in today's lab class, in the lab class, on traversal of trees. Now, how do we count? How do you find the number of leaf nodes in a binary tree? Can be n. So what do we have to do? It's a nice recursive problem. You start the left subtree and the right subtree and keep on augmenting. As soon as you reach a leaf node, you augment a count and return the final value of the